All right, good morning. Happy Friday. It's Friday here for me. I don't know what day it is while you're watching this, but it's Friday for me. We are, I might have to yell at my son here in a second. He's being so naughty. Harry, can you not? He's making eye contact with me. He's trying to lick the food in the sink, which I should clean up, but anyways. So we're gonna do Cryosphere, which I'm very excited about. This is I know I say that every module is my favorite, but this one actually is my favorite module because this was what I got my master's degree in. This was my area of expertise, was studying the last glacial maximum. Um, so let's jump into it. Let's get started. We're going to cover a few topics. We're going to look at ice, glaciers, ice sheets, ice caps, glacial formation, glacial movement. Why do we care about the cryosphere? Paleoclimate and glacial landforms. Here's some vocabulary that you will learn today. So, cryosphere, I feel like many of you have heard the terms geosphere, biosphere, atmosphere, hydrosphere, but cryosphere might be a new one for you. And cryosphere just pertains to the water on Earth's surface that is in a frozen state. Um, it's sort of like that sci-fi prospect of being cryogenically frozen, right? So you can come back in 200 years. Obviously, I think it's a silly concept, but cryo is just frozen. So these are the frozen proponents of Earth's surface that we're going to learn about. We're going to start with ice. I feel like maybe I should have shown this in the hydrosphere module. It might have been a really nice addition, but it's too late now. No takes backsies. Basically, this is the distribution of Earth's water. We're going to start on the far left column here. We have 96.5% of all Earth's water is in the ocean. That's a lot of salt water. It's all salt water, right? We have this 2.5% as fresh water, and then you see a little baby green that are saline lakes and saline groundwater. It's not a lot of percentage. We're going to take this little baby blue section, though, the fresh water, and we're going to expand it into glaciers and ice caps, groundwater, and surface water and other fresh water. So it's basically saying that 1.3% of the 2.5%, so it's not a lot. 1.3% is like rivers and lakes and streams. 30.1% of our fresh water is in groundwater. This is why I'm so sorry, hold on. Harry, get down. Knock it off. Stop it. This is why we use groundwater as our drinking water. And then finally, the rest of that fresh water is in our world's glaciers and ice caps. 68.6% of our fresh water is in glaciers and ice caps. And then over here it says surface water, ice and snow. They're a little bit different than glaciers and ice caps. Ice and snow being annual snow that we see regularly. Glaciers and ice caps are, I don't want to say permanent because they're not permanent, they're all melting, but they're more than annual. So when we look at Mount Baker in the heat of summer and we see that she still has some glaciers up there, those are quote unquote permanent, right? They're not an annual occurrence. They're usually there year round. So a glacier looks like this. I don't know where this glacier was taken, if I'm going to be completely honest. It might have been Alaska, but a glacier is it's a little bit like a river. They form with repeated annual snowfall, and over time, this annual snowfall produces incredibly deep snow that doesn't completely melt in the summer because there are so many layers of this ice. It's a flowing body of ice that flows under its own weight by the force of gravity with topographic help. So you can see that this ice sheet looks like it's flowing through this valley, through this topographic region that might be a river valley otherwise. Perennial snow is the term for snow accumulation that lasts all year. Perennial snow. And there are three general types of glaciers: alpine glaciers, ice sheets, and ice caps. So glacier in and of itself is sort of this all-encompassing term for quote unquote permanent ice sheets. I'm going to stop saying quote unquote, but when I say permanent ice sheets, just know I mean these ice sheets that stay around throughout the year, or they're meant to stay around throughout the entire year. They're not snow that melts in the summer and then comes back in the winter. This is probably Baker. This actually looks like Glacier Peak. This looks like Glacier Peak. Um, so alpine glaciers, they form on mountainsides and they move downward through valleys, just like we saw in that last image. They can create or deepen valleys by pushing dirt and soil and other material out of their way. Alpine glaciers are found in every continent except Australia. Fun fact, Australia has no ice caps, has no glaciers. It's in a weird spot latitudinally, and even though it's a really big continent, it doesn't have any glaciers. An ice sheet is huge. These are continental in size. They cover millions of square kilometers of land, and they may be thousands of meters thick. So this is the Greenland ice sheet. It's the second largest ice sheet in the world. Oh, Earth's largest ice sheets are in Greenland and Antarctica. Antarctica is the largest. Greenland is the second largest. And what I want to say to this is that, sorry, I just had breakfast and now I need to stretch. This week you're going to do a lab, which I love this lab. We're so lucky that Google Earth Pro is so versatile. So you're going to use Google Earth Pro and you're going to look at ice sheets in Google Earth Pro. And the ice sheet you're actually going to look at is the Arctic ice sheet, which is above Greenland. So here's the Arctic Ocean. And the Arctic ice sheet is it's an oceanic ice sheet. So a continental glacier or ice sheet sits over land. And a oceanic ice sheet sits over the ocean. So because of this, the Arctic ice sheet is actually melting substantially faster than the Greenland ice sheet because it is directly in contact with water. The Greenland ice sheet is larger than the Arctic ice sheet. It's the largest ice mass in the northern hemisphere, which with an extensive surface area of over 2 million square miles and an average thickness of up to 1 mile. So in the center here, I'm sorry this picture, I love this picture, but it is really hard to see, and I do apologize. I don't know why they made this blue so light. So on this image, we see this continental glacier, and you see these sort of lines going up. If you go back, if you think back all the way back to hydrosphere when we looked, or I guess geography, when we looked at topographic maps. We were looking at topographic maps with elevation change through contour lines. This is the same thing. So this is telling me that this portion of the ice sheet is the thickest. The center of the ice sheet is always going to be the thickest. This is an ice sheet. Glaciers are a little bit different, and I'll show you what those look like. But this ice sheet is thickest at the middle, so as it gets further to the edge of the land, it gets thinner. Oh, here we go. It looks like this. The Antarctic ice sheet is even larger and covers almost the entire Antarctic continent, and it's thickest in the center and thinner as we get to the edge. So these are just some cross-section views of the Greenland and the Antarctic ice sheet, where the thickness tends to be in the center, and then we get thinner as we go out. Those are thick. That's some thick ice. Ice caps look like this. Oh, this is on Mount Olympus in Washington. So Mount Olympus is the mountain in the Olympic range, the highest mountain in the Olympic range. These are smaller versions of ice sheets. They're very small. Look at this little baby. They usually cover less than 50,000 kilometers squared. They cover high elevations, and they may cover tops of mountains. Oops, sorry. I didn't know. I thought that was more. We see ice caps on Mount Baker and on Glacier Peak as well. They're a little bit smaller than alpine glaciers. Um, let's see if I can find a like this would be an alpine glacier, and then this little guy here, I might consider a little ice cap. It's small, it's round. Um, it doesn't cover a whole lot of space, and we have. Oh, hold on a minute. Okay, apologies because I wanted to put the slide up here. Um, First of all, these are our two friendly neighborhood volcanoes. For those of you who are not familiar with our volcanoes in Washington State, this is the one we see. Well, I don't know if you see it every day. I try to see it every day. This is Mount Bakey. She's beautiful. She's perfect. She can do no wrong. Um, we see her a little bit from a different vantage. This is from the northern side of Mount Baker. And then this is Glacier Peak. We actually don't have visibility of Glacier Peak unless you get down to Everett. She's really tucked into the mountain range a little bit more. But both of these are connected to our stream systems. And both of these mountains, their melt water are our summer drinking water, basically. So I wanted to point that out. And then I wanted to put this slide in here too. I can't believe I didn't put this in here earlier. This is Mount Baker. And we have named her major glaciers. She has 11, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, she has 11 glaciers. I've hiked the Coleman Glacier before. I hiked the Easton Glacier before. But there are all these glaciers associated with Mount Baker. And I think it looks like the Coleman Glacier is the ones directly attached to um, the Nooksack River. Oh, this whole side is. Oh, this is giving. Oh, yeah, this is all connected to the Nooksack. So is this one. And so is. Oh, this whole area is. But I know the Coleman Glacier has a stream that leads directly into the Nooksack River. I've seen it. It's really cool. And Coleman Glacier is melting really rapidly. In fact, these black dotted lines have been the maximum extent of the glaciers in the past. So you can see where they've sort of melted away. We'll talk about that here in a second. Okay, so I put that in a different part of the slideshow, and I'll put this back on canvas. So how do glaciers form? So I showed you ice sheets. Um, Ice sheets are unique in that because they cover entire continents, um, they don't have the same kind of formation as a mountainous glacier does. Basically, what you need to know about ice sheets is that the snow will accumulate predominantly on the center of this ice sheet. Let me go to Greenland here. So the snow is accumulating predominantly here in the thickest part of the ice sheet, right? Which makes sense. And then imagine you take like, what's a good metaphor? I don't know, you take Play-Doh and you smoosh it. Play-Doh's a bad analogy. Imagine that the weight of this new snow that's piling up in the center of this ice sheet is basically pushing the ice outward, which is why it is thinner at the edges than it is in the center. So this ice sheet is being weighted down by more and more snow. So it's like actively pushing this ice sheet out and making the outside more thin. Glaciers form a little bit differently. The accumulation zone is going to be at the peak of that mountain. So most of Mount Baker's snow is coming from the peak, right? And think too about the fact that Mount Baker is considered a rain shadow because she's so high. So once those clouds hit her western flanks, they're going to rise. That water is going to condense and it has to fall as precipitation. But it's up high enough in an elevation that it precipitates out as snow. And so the snow is falling. We get snowfall every year. And Baker's really cool. Baker gets the highest precipitation annually in the world of any volcano or of any mountain, meaning that she gets the most snow every year. And in fact, she broke the world record in like 2018, I want to say, of most snow in one year. Now, just because she got the most snow doesn't mean she's going to keep all that snow. We live in a temperate area, and because of that, she loses a lot of that snow too. So she gets a lot of precipitation, which is also why she's so popular for skiing and snowboarding in the winter. However, she loses that precipitation very quickly too. But if you can imagine, in the wintertime, she's getting these piles and piles of snow. And this is the zone of accumulation, basically. And because of this weight, because of all this new mass, this snow is actually, it's being compressed slightly, but it is also pushing the rest of this glacier down topographic regions. It's sort of moving on its own weight because of gravity. And then the zone of ablation is just where there's no snow building onto this glacier. She is losing snow in this unit of the ice sheet. And these are the only two terms that you need to know. You can look at all of the other terms if you really want, but the zone of accumulation is where we see new mass, new snow piling onto this ice sheet, and the zone of ablation is where that ice is melting away. So, as you can imagine, I talked about perennial snow, where we get annual snow, and sometimes it doesn't all melt. Sometimes you get more snow that sort of layers on top of that. Well, it's sort of like sedimentary rocks in a way. When you have this snow that just keeps piling and piling and piling on top of itself, those lower layers of snow are going to actually start to compress. And when they do that, they become very icy, and they become very clear almost. And so, if you've ever seen the movie Day After Tomorrow, which again, highly recommend, terrible movie. At the very beginning of, I'm pretty sure it's that movie. At the very beginning of that movie, it is that movie. They're taking ice cores from either Greenland or Antarctica, I don't remember where. They're taking ice cores for research. And the cool thing about this ice is it can be millions of years old. And I think the oldest ice is it's only a couple tens of millions years old. It's not built. We don't have ice in the billions of years. That just wouldn't make any sense. But we do have ice in the millions of years. And this is an ice core from Antarctica. When I was at Oregon State University, we had a huge building that was like manufacturer warehouse, large building. And there was a portion of it that was just like cool. It was a little bit like a refrigerator, and we had sediment cores in there. So that's what I studied. But there was a freezer in there too, and you were not allowed in the freezer. If you open that freezer, you can fuck up a lot of these cores. But they stored Antarctic cores and Greenland cores in this freezer. It was so cool. This was one of the cores that they stored. So basically, they core the ice, and the deeper the core is older. Same with sedimentary rocks, right? The law of superposition in that the further you get to the bottom of this ice, the older it is. And you can do isotopic research with this ice, which is why we do it, which gives us paleoclimate information, which we will talk about. But I liked this image because all of a sudden, oh, there's a bug in my house. Well, here you'll find it. Um, there's this dark line in the ice. And this was Greenland. So how did this dark line get here? This was a volcanic eruption. And in fact, this was the eruption of Mount Mazama. Gosh, we're module 6 now. Are we past the national park? Well, we're at least far enough for you to know that Mount Mazama is modern day Crater Lake. So Crater Lake National Park in Oregon used to be a giant volcano, and it erupted 5,500 years ago. And this eruption was massive. It was like 20 times the scale of the Mount St. Helens eruption. And because it was so massive, the entire world got ash layers just deposited all over it, which is really cool, because this gives us, remember how I was talking about index fossils? This gives us a line or an index fossil, so to say, of we know that this portion of ice is exactly 5,500 years old because that was the Mount Mazama eruption. And what's cool about the Mount Mazama eruption is because we have this layer of ash everywhere, it sort of gives us this stratigraphic continuum throughout the world. That's so cool. So if we find a line of Mount Mazama ash, and we can chemically date that, we can say, okay, well, this is a line of ash, but what is it? We can date it. It would match with Mount Mazama's chemical signature, and we would say this was Mount Mazama. So this stratigraphic line is 5,500 years old. So cool. This is just another diagram of glacier formation, where we see the accumulation, we see it flowing, and we see ablation down here. We see it melting into the ocean or into the ground. Glacier movement's really interesting, and I always kind of giggle. I don't know if you've seen Frozen 2. Love Frozen 2. Unpopular opinion, it's better than Frozen 1. Um, and also, spoiler, sorry, Elsa finds this magical island where she discovers how she got her magical ice powers. And it turns out to be a glacier. And she's like, glaciers are rivers of ice. And I have to admit, I don't love this term because rivers are flowing bodies of water that move in a liquid state. And I think that it makes sense to say that glaciers follow topographic contours in the same way that rivers do, but glaciers don't necessarily move in the same way that a river does. In fact, because it's solid, it has entirely different properties as it flows. So I'm going to play this. I'm actually going to shut off the. Can I shut off the? I don't want volume. Okay. Oh, here it was. Ha, Emily. Okay. So this is a video and it's linked in YouTube. So if it kind of shows up funky on this video, because sometimes I feel like when I show videos on my screen share for this, it doesn't work, but it's on here. I started at 50 minutes and it's a time lapse. And again, it is following. Okay, wait, I want to pause here. It's following lines of topography down a mountain slope. But what I want to point out is these cracks. So these are crevices of this flowing body of ice. And this is how this sheet flows. It flows like it flows more like a non-Newtonian fluid, I would say, than it does liquid. Which is why I'm like, rivers of ice, that's not a great term. Hi, Hannah. But uh so as it moves, it cracks and it shifts and it changes. It doesn't really, I don't know if I love the term flow. I guess you could say flow, but I just feel like there's better words for it. It like chunks down. It slides down. You know, it's slide. I like slide. Slide is good for now. Under its own weight, following topographic changes. Hi, sweet angel baby. And it is really cool. And you had to watch a little bit of a snippet of ice uh, for the hydrosphere module. Okay, couldn't hear my. Did you have to? No, I don't think I made you watch that video. Never mind. I didn't make you watch that video. You guys had a different one. There's a video that talks about how glaciers move as well, how fast they move basically, and they don't move very fast. That was a time lapse video. So why do we care? Why did I put this module in this class? Other than I love it and it's my favorite, right, Henny? Because it is going to play a role in all of the spheres because we're all connected. And it's an integral part of these spheres. So I'm going to bring us back to hydrosphere. This was the global surface salinity map that you saw. And in that module, I discussed briefly the Greenland ice sheet and how it is melting here. It is freezing it in this area, but it is also melting. And this melting is contributing to the map of the ocean conveyor belt. So forgive me if you watch Day After Tomorrow, which I love hazard movies. They're so good. if you watch The Day After Tomorrow, basically what happens is this guy is suggesting that this current is changing in the Atlantic, and because this current is changing, it's changing the climate dramatically. And the silly thing about that movie is it's happening all so fast and so rapidly, and that's just this. It's such a silly take. We would have years of notice before we realized that this was going on, but this portion of the conveyor belt starts with the meltwater from Greenland. It's incredibly important. It forms the deep water. Here, I'll go back. It forms this blue strip here, the deep water formation in the Atlantic Ocean, which contributes to much of the currents throughout the entire world. And it starts here in the Greenland North Atlantic area. So basically, if this ice sheet melts fully and we no longer get this deep water formation, this could actively alter a lot of subsurface, oh my God, I can speak, I promise, subsurface flows, which would alter climate. Why? I literally had you here and you were like, absolutely not. I need to stand in front of your computer and interrupt your lecture. Okay. So that's why a lot of this cryosphere is so important, but it's so more important for other reasons. If we lose the ice caps on Mount Baker, we lose a lot of our summer drinking water, which means that we could have a water crisis. I don't necessarily fear that that's going to happen in the next few years, but it is an issue looking into it in the next 50 to 100 years. This is a diagram of the last few hundred years. This is global mean sea level. So this is how the sea level has risen, and it looks really dramatic. Keep in mind, oh my God, Henry, I love you so much. Keep in mind, our units here are in millimeters. So if you have a ruler, I don't know if I should have a ruler. Here's my ruler. Where's my camera? So, let me, and Henry's butt. Henry, stop. So you see the numbers 44. Oh my God, I can do this, I promise. 44 and 45. That is a centimeter. So all those little lines between 44 and 45, if you have a ruler, that's a millimeter. So while this graph looks very dramatic, what we're saying is we're going from 0 millimeters rise in 1880 before the huge burst of Industrial Revolution, and then we're rising 200 millimeters, which is still a lot. Oh my God. But it would be, let me see if I can do 200. Hold on. I don't want to sit here and figure this out for the next 5 minutes, so I'm going to pause. Okay. 200 millimeters is from this finger to here. It's 20 centimeters. So this, again, looks very dramatic. It's not necessarily dramatic perspective. Oh my God. I need to start doing this at school. This is Harry. I don't know if we've seen Harry yet. Come here, babe. Come say hi. So but in perspective, it's not a lot, but it is a lot. And that's just average. So if all Greenland's ice sheet melts, the sea level will rise 7 meters. That's wild. That's a huge difference. If all of the Antarctic ice sheet were to melt, the sea level is going to rise 60 meters. And this is the trajectory that we're on with climate change, which is in 2 modules from now. So one of the things that, oh, my sweet baby mother of God, stop. One of the things that I got to do, and the reason that I studied ice sheets in the last glacial period was to study the paleoclimate, meaning that I studied the climate for this area that was 20,000 years ago. This is called paleoclimate. This is the study of historical climate, and it's incredibly important because this leads us to a better understanding of modern climate. And to understand this, we're going to look at what we call Milankovitch cycles. There's 3 cycles, and we've already seen one, but surprise, you didn't know you did. We looked at obliquity. I don't remember what module, I apologize. Basically, we looked at the fact that the Earth isn't sitting exactly up and down. It's sitting at a weird angle of 23.5 degrees, which is why all of our globes are sitting at like weird angles, because that is the angle at which our Earth is sort of tilted. That's called obliquity. We look at precession, which is sort of the wobble of Earth's tilt. But what I'm going to focus on for this is called eccentricity. And eccentricity is basically the orbit around the sun. Historically, it hasn't stayed the same. Earth's orbit doesn't stay the same. It changes from other reasons, for other reasons, other gravitational reasons. I'm sure there's math that goes into it that's like the planets have something to do with it, Jupiter's pull has something to do with it. I don't honestly know. But there are a lot of factors that go into this. And what it means is that sometimes our Earth orbits around the sun in a like an oval shape, like an egg shape, meaning that at some times during the year, because if you orbit the sun fully, that's a year, the orbit is further from the sun than it is in a perfect sphere. And right now, we're orbiting the sun closer to it being a sphere. We're like somewhere in between it being an oval and a sphere. So we're not quite as far from the sun in this ovally shape. But there are times in history where we see that the Earth can be in this very dramatic oval shape, meaning that in some portions of the year, it's very far from Earth's sun. And this change occurs about every 100,000 years. Now, if you imagine if the Earth is not quite as close to the sun, it's going to be colder. So the periods in which we have more of this oval-shaped orbit are the periods that we have seen ice ages. So we have this glacial and interglacial cycle. Interglacial just means periods of Earth history where there were no glaciers or minimal glaciers. And then glacial meaning a period of Earth's history where we saw glaciers. So this graph depicts Earth's time about 450,000 years ago, pardon me. And just in this time period, we see an interglacial and a glacial period and an interglacial and a glacial period. This is our average temperature in Fahrenheit from today back to 45 or 450,000 years ago. So we've had a few glacial periods. We've had 4 glacial periods and 5 interglacial periods. We're technically, it says we're in an interglacial now, but what you'll know is that this interglacial is not quite as warm as this interglacial. And I think a lot of glaciologists, myself included, would say we're still kind of between a glacier and an interglacial. Like we're technically still in a glacial period because we have these continental ice sheets on our poles. An interglacial basically depicts no ice sheets at all in Earth's history. And an interglacial, we believe, occurred 55 million years ago when the Chuckanets were deposited, because the Chuckanets were such a tropical uh, riverine system in the same latitude that we believe that it was probably an interglacial period. So 20,000 years, I guess let me go back here because this was about 20,000 years ago, this little bloop here. We were in a maximum glacial period. And this maximum glacial period was this. This is the Cordilleran ice sheet. The Cordilleran ice sheet sat over Washington, the northern parts of Washington, Idaho, and Montana. And the entire period itself lasted about 100,000 years. So if I go back again, boop, it lasted about 100,000 years. We had this little bloop of warming period, we believe, 50,000 years ago. But the last glacial maximum, which was the period that I studied for my master's degree, looked like this. This was the last ice age's maximum extent, meaning that this ice sheet went down a little bit further than Olympia here in the Puget Sound. And look at this lobe here. We call this the Puget lobe. Yeah, okay, we will look at this, but we call this the Puget lobe, and it basically defined the Salish Sea area. This is one of the reasons that the Salish Sea looks the way that it does. So when this ice sheet receded, it would form lakes within the continents. But the really cool concept about these ice sheets is that it didn't just come all the way down and then melt. We know that this ice sheet came and advanced over this area and then it would melt. And then it would advance again over this area and then it would melt. And then it would advance over this area again and it would melt. We think this happened like 50 times just in the last glacial period alone. So we saw a lot of glacial scouring in this area. I'm going to talk a little more about that here in a second. But I want to show you, I'm going to go back because we have all this ice sitting over this continent. And so this was just over Washington, Oregon, and Idaho. We had a massive ice sheet that sat over all of Canada. And we had the Laurentide ice sheet that sat over the uh, the eastern part of the United States. And this was just the United States. I don't have a depiction of the massive scale of ice that was over the northern part of the globe. Go. Um, but what this means is, if you remember in the hydrosphere module, fresh water is what makes up these ice sheets, right? So if fresh water is making up these ice sheets, what this is saying is that our sea level was significantly lower during these ice periods. So about 20,000 years ago, this was the extent of our land. Our ocean was much lower. So the continents had a lot more exposure. So this was like Florida was huge. Look at that. This was like a lake. I don't actually know what was going on here. I have a good depiction of Washington's coastline. So during this ice maximum, this orange line here was about the coastline during the Ice Age, which is so cool. How wild is that? That's almost to uh, the boundary line, the plate boundary line. So it was a massive scale ice sheet that had so much water in it. And then as this ice sheet melted, it rose. The sea level rose. Sorry, that came out weird. The sea level began to rise. But this is a natural process. Like this has happened so many times throughout Earth's history, that it is a natural geologic process of ice sheets and no ice sheets. We are headed towards another interglacial period. And what I'll say to that is when I talk climate change, in a couple modules, I mentioned like, yes, we're losing our ice caps because of it. And yes, we're supposed to be losing our ice caps because we're headed towards a more interglacial period, but we are losing these ice caps at a rate that is much faster than we've ever seen these ice caps melt in geologic history. So that's the difference when people are like, well, the ice sheets are supposed to melt because we're in an interglacial. Yeah, I agree. But we're melting them at a much faster rate than is A, sustainable for humans, but also much faster than we've seen historically. This was in this area. So this was my research, basically. So of course I put this slide on here. The Puget Lobe sat over Puget Sound. What's in the next slides? Okay, we can talk about this. The Puget Lobe sat in the Sailor Sea over the Puget Sound, and it carved out much of Puget Sound. My work pertained to how the ecology of this area changed during this time. And what we found was when there was ice sheets over the Puget Lobe, we found ferns and shrubs. And it wasn't until the ice sheet receded entirely that we began to see full-grown trees in this area. So a lot of our modern day trees, including the red cedar, including the spruce, these didn't arrive until 20,000 years ago. In this area, and I taught a class this spring. It was one of my favorite classes I've ever taught. I had such incredible students. I got to do a research project, and I'm going to do it again this next spring. We're going to do a research project for my Geology 208 class. And the research project I chose to do was studying the glacial landforms of this area. So when a glacier moves, it scours out that terrain. These ice sheets were so big and so deep. So the The ice sheet that sat in this area, in the Puget Sound, the Puget Lobe, in the Skagit area was about 2 miles thick at its maximum extent. So we were sitting under 2 miles of ice, which is the same amount of ice that is currently on Antarctica right now. We were sitting under 2 miles of thick ice. And now, if you can imagine, as this ice sheet flows, slides, as it slides, it picks up boulders, it picks up pebbles, it picks up cobbles, it picks up sand, it picks up silt, it picks up any type of sediment that it can. Sometimes it scours it off of bedrock entirely, like just plucks it off of bedrock. Sometimes it pulls it from loose material. And the base of this glacier then becomes an incredibly coarse grit sandpaper, basically, because you have all of this unconsolidated and unsorted till, we call it till, sitting at the base of this glacier. And again, it's pebbles, it's cobbles, it's boulders. And because of this, as the ice sheet continues to slide, it is scraping out this area like sandpaper. And so it leaves behind this really beautiful evidence of where it was, basically. And in this area, we have glacial striations. So this is probably a little bit further south. I think this is in Puget Sound. But you see these parallel delineations in the Puget Sound. This is from the last glacier. We also have some in this area. Lopez Island, that's me, has these beautiful glacial striations. This is a boulder, and basically the glacier scoured out this line here and deposited this boulder. This was under the ice sheet 20,000 years ago. We called this a glacial erratic. It was melted, it was left here after the glacier melted. The glacier probably dragged it from Canada all the way down to Lopez. And actually, this area was down here. This was Iceberg Point. You can see these incredible striations in Iceberg Point. This was another one. This one was weird, and I like this one because it has a weird, like, corkscrew vibe to it, and I can't figure out how this happened. But this was another glacial scouring. And then this is a really good depiction of a glacial scouring here, where this was sandstone, so it's sedimentary rock, so it's relatively soft. So this glacier moved through this topography and scoured out the side of this rock with a boulder that was stuck in the ice lobe and scraped it down. This is a glacial striation. We see other landforms. This is a picture of Mount Rainier in Seattle, and I love this picture because this is where this glacier used to be. So this alpine glacier used to be all the way down here, and we know this because it scoured out this part of the mountain. These are called moraines. This is a lateral moraine, this is a lateral moraine, and it's almost like a river valley, right? But it's not, it's a glacial valley. And there's one up at Mount Baker as well. This is the Easton Glacier. This is Bakey. This is the Easton Glacier, and you can hike along this ridge on Mount Baker, this moraine ridge, and it's horrifying. So this is on one side, there's a beautiful meadow on this side, and then on the other side is a sheer cliff. It's really cool. Highly recommend this hike, actually. It's beautiful. This is the Railroad Ridge hike on Mount Baker. It's tumultuous to get up there. It's a tough one. I will say that it was not an easy hike, but it's a beautiful hike as you get to this incredible moraine that was left behind from a glacier. So this is where Easton Glacier is now. But at one point, Easton Glacier was all the way up here scouring out this mountainous terrain. So the cryosphere is a really incredible entity. And we're losing a lot of ice to climate change, and we're going to talk about that at the climate change module. But next module is anthroposphere, which is another fun one. So I'll see you in a week.